Here we have the first practice question. A plane mirror is placed 22.5 centimeters in front of a concave mirror. So that means we have the distance between the two mirrors, which is 22.5 centimeters. And the concave mirror's focal length is given as 10 centimeters. Find where an object can be placed between the two so that both the final image and object coincide. Now Jai will continue with the solution.
Now, we'll first analyze what is the setup of the question. So, basically, there is a concave mirror. Uh, there is a plane mirror whose distance from both distance between both of them is 22.5 centimeters. Let this be M, this be P. Now, and this the focal length is 10 centimeter. Now, it is given that an object is placed between the two, so that the final image and the image coincide. So basically, let there be an object O with position O, and the distance of this from the concave mirror be x. So the final image formed by this object by both the mirrors should coincide with this. That is, if after reflecting from the plane mirror, thereby again reflecting from the concave mirror, the final image should form here at the object position only. So basically, our distance MO is 22.5 minus x, and let there be an intermediate image formed by the object by the plane mirror, which is somewhat here. Now recall that we learned that the image distance and object distance in a plane mirror are same. So MO and I dash M are same, which is equal to 22.5 minus x. Now we will employ one of the most basic concept which light has, and one of the most phenomenal properties that light has, which is the reversibility of light. So basically, what does reversibility of light says that if the light travels from an start point to a source point, the same path will be followed by when the light travels from the end to the source point. So basically, we can treat the final image as a source to get the intermediate image. So basically what happens, we first get the intermediate image distance, with then we will put the final image distance and the intermediate image distance, that is I dash, in the mirror equation, and we can get the value of x. So let's proceed with that. So as we got I dash M equals to MO equals to 22.5 minus x, so this implies IP is equals to 45 minus x. Now, as the final image formed by the I dash coincides with O by the concave mirror, so we just apply the mirror formula. And remember to use the Cartesian sign properly. And what does the Cartesian sign says? That the direction of incident light is taken to be positive. So basically the object is here and the direction of incident light is there. So distance measured from here to here are taken as positive. So now we apply 1 by V plus 1 by U equals to 1 by F. Now for here U is the distance of the intermediate image from the concave mirror, and so U will be equals to minus 45 minus x. Remember, U is the distance from here to here, so it is in direction opposite to the incidence light, so this should be negative, so that's why we have taken as minus 45 minus x. And as we know, the final image formed coincides with the object, so the V should be equals to minus x. So this is V is equals to minus x. Now we will simply plug in the values in the formula. So 1 by V is 1 by minus x plus 1 by minus 45 minus x is equals to 1 by minus 10. Note that the focal length of the concave mirror is negative, as the focus of the concave mirror is situated here. So, and it is in the opposite to the direction of incident light. So the focal length is negative. From here, we get a quadratic equation in x, and we get two values of x, which is equal to 30 and 15 centimeters. Now, in the question, it is given that the object is between the mirrors. So x should be less than 22.5 centimeter. So, which gives the values of a single value of x as 15 centimeter.
So, to summarize this question, first we started by noting the data given, which is f, which is the distance between the two mirrors, 22.5 centimeters, and the focal length of the concave mirror, 10 centimeters. Then we do a setup of the given situation. Then we applied the concept of reversibility of light, that is the object that is the light coming from the object and reflecting to the final image can be, the path of this is the same as the light coming from a source and then going back to the object. Then after that we assume this object to be placed at a distance x from the concave mirror, and then we got the intermediate image position through the plane mirror, and then we simply applied the mirror formula for the concave mirror with the final image coinciding with the initial object. By applying appropriate Cartesian signs, we got this equation, and then from the values we reduced it to the single value by looking at the conditions given, which is that the object should be placed between the mirrors. In this question, there is a concave mirror and the setup is shown in which an object is placed in front of it. The object's initial position, the initial distance from the mirror is given as 30 centimeters. The mirror's focal length is given as 20 centimeters. Now, the object has a velocity of 15 meters per second at an angle to the principal axis, that is 53 degrees. Also, the concave mirror has a relative motion and it moves at a speed of 2 meters per second towards the object. Now we have to find the velocity of the image.
So this question basically involves two concepts: the concepts of relative velocity and the concept of concave mirror. So basically, first we'll choose a coordinate system so as to make the process easy. We will first choose this as x-axis and this as y-axis, the positive x-axis and the positive y-axis. Now we will resolve in the velocities of object and mirror into its component. So let's say velocity v of an object, the vector v of an object will be given by 9 I cap plus 12 j cap, and the velocity of mirror will be given by minus 2 I cap. Now, so the relative velocity of object with respect to mirror is given as velocity of object minus velocity of mirror, which is equals to 11 I cap plus 12 j cap. Now, for considering the we will consider the individual velocities. We will consider the velocities of different axes as a different part. So basically, the two motions are considered as a different, and so we will proceed. We will calculating the motion along y-axis of the image differently, and we will calculate the motion along x-axis of the image differently. Now, As you know, we have discussed about the lateral magnification in case of a mirror, in case of a concave mirror. So the lateral magnification can be related to the velocity of the image and the object along the y-axis. So basically, we could say that the lateral magnification mm, m, which was given by hi by height of image by height of object, is equals to the velocity of the image at y-axis by velocity of object at y-axis. So So, and now we will consider the motion along the x-axis. Now for calculating the velocity along the motion on x-axis, we need to consider distances along x-axis. For that, we could consider only one form. We could rely only one formula, that is mirror formula, which is given as 1 by v plus 1 by u is equals to 1 by f. So by differentiating both sides with respect to time. So by differentiating both sides with respect to time, we will get velocities along x-axis of both the image and the object. We will get velocities of the image along the x-axis by plugging the value of the velocity of the object along the x-axis. So let's differentiate it. We will get as dv by dt into minus 1 by v square plus du by dt into minus 1 by u square is equals to 0, as for focus is constant. So from this we will get dv by dt is equals to minus m square du by dt. Now as we know that m is equals to velocity, m is equals to v by u. Now so this will give me as velocity of image along x-axis is equals to minus m square velocity of object along x-axis. So now as we got everything in terms of magnification, now we need to find the magnification of the above setup. So as we have discussed in the theoretical, the magnification can be given by the focal length, by the difference of focal length and the image distance, which will give us magnification as -2. So after putting the values of magnification in the above equations, we could get the values of different components of velocity of images. So velocity of image along x-axis is given by -4 into 11, which is equals to -44. Velocity of image along y-axis is given as -2 into 12 is equals to -2. Now in this, all the velocities which we considered were relative to the mirror. So basically what we obtained here are the velocities relative to the mirror along the coordinate axis. So basically the final velocity of the image is given as the velocity of image that we got with respect to the mirror, which are this plus velocity of the mirror, which will give me as -46 I cap -24 I cap.
third question is described as follows. When the beaker is empty, the observer could see the top of the rod. So from the diagram, we see that we can form a triangle from which we can obtain some data. Now the beaker is filled with liquid with refractive index mu up to a height of 2h. Now we have to find mu, that is the refractive index of the liquid, such that the observer could now see the bottom end of the rod. We are also given that the radius of the beaker is h. Now Jai will draw the diagrams and explain the solution to this.
So this problem doesn't involve much of a memorization and all. It basically involves a basic concept of the Snell's law and the use of geometry to calculate the various sign and the various trigonometric ratios of the angles. So in the diagram we could see that when the liquid is filled up to a height 2h, the incident ray, the path of the incident ray reaches up to the top of the rod. Now, when the liquid is filled up to a height 2h, uh, the ray inside the liquid goes to the bottom of the rod. So, which means that the incident ray, after striking the surface, is refracted in such a way that the refracted ray now reaches the bottom of the rod. So, here this is the normal. We see this is the incident ray, this is the refracted ray. Now we apply basic geometry. We saw that the radius of the beaker is h. This height is h. So this total height is 2h. So this height must be h. And since the observer could see the top of the rod, so this height is, and since this length is 2h and this length is total is 3h, so this should also be 2h. So this angle is 45 degree. We got that this angle is 45 degree. Now we see basically the cells now, which says that sine I by sine R is equals to the mu. Here mu will be equal to the mu of the liquid. So basically now we in this question only involves the calculation of the trigonometric ratio of like sine I and sine R. Now we will basically proceed how we could use the geometry in this. Now we could see that this angle is 45 degree. So by simple geometry we could see that I is equals to 45 degree. Like this is 45, this should be also 45, then 90 minus 45, I is also 45. Now for calculating R, we need just for calculating R we need to know, for calculating sine R we need to know what we need to know the perpendicular length and the hypotenuse. So we know now we consider this triangle, this. Now in this, the perpendicular length is h and the hypotenuse is this. Now the base of the triangle is of length 2h. So we get the hypotenuse to be root under 2h square plus h square, which is equals to root 5 h square. Sorry, root 5 h. So sine R is equals to h by root 5 h, which is equals to 1 by root 5. So mu is equals to sine I, which is sine I by sine R, which is sine of 45 degree, which is 1 by root 2, by sine of r, which is 1 by root 5. By this we get mu is equals to root 5 by 2.
So, to summarize this question, let us consider the following. First, we drew the final diagram of how the refracted ray would look like when the liquid was there. Then, we obtained the incident angle I by using the initial diagram, which is this triangle. Then, after that, we went on to the refracted angle by considering the final triangle, which is this one. Then we simply applied Snell's law and then found out mu liquid, which is equal to sin I by sin R.